All right, so I'm going to start out with defining static equilibrium. So, static equilibrium. What is it actually saying? So, we have the two words static and equilibrium. Static tells us that the object isn't in motion, and that's rotational motion and translational motion. That means that our velocity is zero, acceleration is zero, and as I said for rotational mechanics, our omega is zero, and our alpha is zero, and that's rotational velocity and rotational acceleration. Now, equilibrium, that means that everything is balanced for the system. So that's saying that the sum of our forces equals zero, and that the sum of our torques equals zero. So it's just saying the two words static equilibrium actually gives us a fair bit of information, and we can use that to problem solve. All right, so we are given that system over there where you have, actually I should label wall, where you have a thin metal rod coming out from a wall, and it's attached by a screw and being held up by this rope. So it's attached to the wall at 2 points through the screw and through the rope. And we're asked what shear force Fs and normal force N must the screw withstand. That means that we want N and Fs, and I didn't write this, but in this case we're given the mass of the rod, we're given the length of the rod, and we're also given theta. So how do we approach this? Now, the system is in static equilibrium. So as I have written over here, static equilibrium means that it's not moving and that everything's balanced. So we can use that to find what we want, which is N and shear force. So I'm just going to start by drawing a quick little force diagram of the rod. So that's our rod, and then it's being pulled down at its center of mass with force mg. That's just the force of gravity, and then there's also the tension from the rope, which is acting over theta, tension from the rope, and then for the screw, shear force runs parallel to the wall, so that's shear force, and then we have a normal force, kind of hard to see. We have a normal force and coming coming towards the rod, out from the wall into the rod. Because there's some force equals zero, that also means that the components of a force equal zero. So the sum of the forces in the x direction equals let's see here. So in the x direction we just have normal force pointing to the left. Oh, sorry, I should define this. I'll define this as up is our positive y, and to the right is our positive x. So n is going the negative x direction, and then tension, the cosine component of tension is going in the positive x direction. So it means that we have e cosine theta minus n. And remember, because it's at static equilibrium, I mean that net force equals zero. That means that this equals zero. And now let's do the same thing for our y components. So we have the sum of forces in the y direction equals, so since it's defined as up being our positive y and down being our negative y, we have, for positive, we have the shear force going straight up. So I'll write that. We have the sine component of our tension, uh, that right there, the sine component of our tension. We'll do T sine theta. A pretty bad theta. Hold on. I'm not using the best chalk here. T sine of theta, and then the only y component force that we have going in that negative direction is mg. So I'll put minus mg at the end, and that's also equal to zero because static equilibrium, net force equals zero. So we're going to circle back to those later. I just want to have those written down because I'm going to be erasing this force diagram. So in order to solve a problem like this, we're actually going to try and find tension. And the reason we're going to try and find tension is because if you look in our x components, we're we have two unknowns, tension and normal force. Normal force is one of the things that we need for our answer. And then our y components, we just another two unknowns, tension and shear force. And shear force is another thing that we need for our answer. So it makes sense to find tension first. But how do we find tension? Because here we have two equations, both of them with two unknowns. We can't solve that. We need to use torque in order to find tension. So we're going to pick a pivot point or a fulcrum, as you could call it, for our system here. And we have two options. We can either do A, which is right here, where the rope meets the end of the rod. We can either do B, which is right at the center mass of the rod, or we can do C, which is right where the screw meets the rod, or where the rod meets the wall. The sum of the torques at A equals the torque from the shear force, which is pointing up in the counterclockwise direction, which means that's positive, and minus the torque from gravity, which is the gravity pulling down on the rod. And then we also have for B, it would be the shear force minus the torque from the shear force minus the torque from the tension. And then for point C, it would be the torque from gravity minus the torque from tension. Now, all these equal zero because static equilibrium, our net torque equals zero, meaning that at any point that we pick to use for torque, our torque equals zero. Um, so for how do we pick here? For point A, we have one unknown, which is just the torque from shear force. For point B, we have two unknowns, which is the torque from tension and the torque from shear force. And at point C, we have one unknown, which is the torque from tension. Now, remember earlier how I said that we want to solve for we want to find tension because with tension we can solve for a normal force, which is one of the things we need, and our shear force, which is the other thing that we need. The only one of these that has one unknown and has tension in it is point C. So we're going to be using point C. All right, so the sum of the forces, or the sum of the torques at point C equals the torque from gravity, which is relative here, is pulling the whole system counterclockwise. I mean, that's positive, minus the tension, which is pulling the system clockwise, which is negative. So we can rewrite this as 1/2 L mg minus LT sine theta. So we have 1/2 LMG minus LT sine theta. This is also equal to zero, so we can rearrange this to set these equal to each other. So that'd be 1/2 LMG equals LT sine theta. Cancel our L's, and if we rearrange for tension, it comes out to tension equals mg, divide the sign over 2 sine theta. All right, so that's our tension, and now we can use that tension to solve for normal force and for our shear force. All right, so let's start with finding our normal force. So we already have t cosine theta minus n equals 0, so we can rearrange that to be n equals d cosine theta, and then when we plug in the tension that we just solved for, that comes out to mg over 2 sine theta times cosine of theta. Now we can pull this sign out and rewrite this as mg over 2 times cosine of theta over sine of theta. And then cosine over sine, that's just cotangent. So you can write that as cotangent theta. And that's our normal force. So we have n equals mg over 2 cotangent of theta. All right, now let's do the same thing. Let's plug in tension into our y component. So we can rearrange this top equation for a shear force, F shear equals, let's see, add the mg minus the t sine theta, so it'd be mg minus t sine theta. Plug in tension, uh, yeah, you plug in the tension that we saw for, and you get mg over 2 sine theta times sine theta. Those signs cancel out, and then so then we just have mg minus 1 half mg, and then mg minus 1 half mg, that's just 1 half mg, and that's our shear force. And that's our final answer because we just need normal force and shear force, and then now we have both of them. So in summary, we started out by writing out our force components, seeing that we need tension to solve for both the forces that we need for a final answer, and then we use sum of torques equals 0 because the system is in static equilibrium. We use the sum of torques equals 0 to solve for our tension. And then we plug that tension, also using static equilibrium because the sum of forces equals 0, plug that tension into these components and then solve for our shear force on the screw and the normal force.